Hi everyone, my name is Bai Li, and I'm from the University of Toronto. And today I'm presenting my work called Representation Learning for Discovering Phonemic Tone Contours. So the problem that we're solving is unsupervised tone clustering. So given a list of spoken syllables in a language that has tones, like Chinese, can we use an algorithm to automatically identify which syllables belong to the same tone and what do the tones look like? So the reason that we want to solve this problem is because one of the first steps to understanding a language is figuring out the sound categories of the language. And in this paper, we use unsupervised neural networks to solve this problem in two tonal languages. First, Mandarin, which has 4 tones, and Cantonese, which has 6 tones. The data that we use consists of 400 words in each language. Each word is between 1 and 4 syllables, and within each language, the same speaker speaks all of the words. First, we'll use Prat to extract all the pitch contours using the default settings, and then we manually segment them into individual syllables for the neural network to use. Next, let's talk about the model. So first, we have a convolutional autoencoder. It consists of 2 convolutional layers into a hidden representation of 2 dimensions, followed by 2 deconvolutional layers. And we train this to reconstruct the original pitch contour. And this learns a hidden representation for each pitch contour. Now, after this has been done, we next apply PCA on the hidden contours, and we run mean shift clustering. Now, finally, we feed the center of each cluster into the decoder, and this gives us a prototype pitch contour for each tone category. Now, let's talk about mean shift clustering. The reason the way mean shift clustering works is it estimates a density function, and it iteratively moves the center of each cluster towards the area of high local density. And the advantage of doing this over other clustering methods is first, this is guaranteed that the cluster centers will be an area of high density, so that when we generate the pitch contours from the cluster centers, it will be an area where there are a lot of neighboring points. And second of all, it's not as affected by outliers than other methods like k-means clustering. So here are the results. On the left-hand side, we have Mandarin, and it generates 4 clusters with the pitches that are pretty similar to the 4 tones in Mandarin. On the right-hand side, we have Cantonese, and the 5 clusters that are generated is not quite the same number as it's supposed to be. In Cantonese, they're supposed to be between 6 or 8 tones, but we give an analysis of how do these clusters correspond to the ground truth in Cantonese. So how do we select the number of clusters? Well, this is a little bit tricky question, but we give a heuristic. So here we plot the size of all of the clusters, and we see that there are a few big clusters in each language and a bunch of very small clusters. And we assume that a plausible cluster has to be a certain size, and if it's less than this size, then it's probably a spurious one that's just noise generated by the clustering algorithm, and we discard those and treat them as unclustered. So for evaluation, we evaluate the normalized mutual information between the cluster labels and the ground truth. The reason we do this instead of accuracy is because this allows us to have a different number of clusters generated than the ground truth. And on the left-hand side, we have the NMI for the autoencoder model. On the right-hand side, we have a baseline, which is first extracts 2 engineered features: the mean slope, the mean pitch, and the slope of the pitch of a syllable. And we run k-means clustering on that representation. And interestingly, we find that in both languages and for both models, we have better performance when we use the first syllable than if we use all of the syllables. And this is because the first syllable is less affected by contextual effects. So let's talk about what this means. This is one of the challenges of contextual effects, where a syllable sounds different depending on the context. So there are two types. First, the carryover effect is when the pitch contour is different depending on where the previous syllable pitch ends up. If its previous syllable is high or low pitch, will affect how current syllable turns out. And the second contextual effect is declination. So typically, the pitch of utterance starts out high at the beginning and then goes lower and lower. And this is a common effect cross-lingually. And another challenge is it's really hard to distinguish between allotones and contrastive tones. So what this means is sometimes when you have the same underlying tones, it comes out as different forms depending on the phonetic environment. So, for example, in a lot of Chinese dialects, when you have a voiced initial, the tone is lower pitch than when it's a voiceless initial. And it's hard to tell whether we should treat this as two different tones or variations of the same tone. And generally, this is done by looking at whether there exists a minimal pair. And without this information, it's not really possible to do this. Let's conclude. So in this paper, we used neural networks to discover tone categories from a list of spoken words in a tonal language. And this is a first step towards understanding spoken language without supervision. I hope you learned something from this talk, and thank you for attending.